For performance task number 1, calculate the line current required for a 30 kW 3-phase motor having a power factor of 0.85 lagging, if it is connected to a balanced source with a line voltage of 440 volts. Our given is real power P equals 30 kilowatts or 30,000 watts, power factor with the formula of cos theta P over S equals to 0.85 lagging, line voltage VL equals to 440 volts, and our formula, apparent power S equals square root of 3 VL times IL. We will transform the formula to get the IL. IL equals S over square root of 3 VL. To get the value of S, we know the formula for power factor. Power factor equals P over S will be transformed to S equals P over PF. Our S is equals to 30,000 watts over 0.85 is now equal to 35,294.1177 watts. Now we will get the line current IL with the formula of S over square root of 3 VL is equals to 35,294.1177 watts over square root of 3 times 440 volts. Our line current is now equal to 46.3115 amperes. In number 2, assume that the two balanced loads in figure 3 above are supplied by an 840 volt RMS 60 Hz line. Load 1 is Y connected with 30 plus J40 ohms per phase, while load 2 is a balanced 3-phase motor drawing 48 kilowatts at a power factor of 0.8 lagging. Assuming the ABC sequence, calculate A. The complex power absorbed by the combined load, B. The kVAR rating of each of the three capacitors delta connected in parallel with the load to raise the power factor to unity, and C. The current drawn from the supply at unity power factor condition. We have a given line voltage of 840 volts, real power for load 2 with 48 kilowatts, and the impedance of 30 plus J40 ohms. The complex power S1, we have the formula VL squared over conjugate of impedance Z is equals to 840 squared over 30 minus J40 ohms. Now our complex power S1 is equals to 8.4672 plus J 11.2896 kilovolt ampere. For our complex power S2, we need to get the reactive power Q2. Q2 equals P sub 2 tan theta sub 2 is equals to 48 kilowatts tan cos raised to negative 1 0.8. 48,000 watts tan 36.8699 is equal to 36 kVAR. Now for our complex power S2, we have the formula P sub 2 plus the reactive power Q2. 48 kilowatts plus J36 kVAR is now equal to our complex power S2 48 plus J36 kilovolt ampere. For the total power ST, we have to add them up. S1 plus S2 is equals to 8.4672 plus J11.2896 plus 48 plus J36 kVA is equals to total complex power 56.4672 plus J47.2896 kilovolt ampere. Now we have the total complex power of 56.4672 plus J47.2896 kilovolt ampere. We will convert it to its polar form. which is 73.6536 bar angle 39.9452 degrees kilovolt ampere. We can also get its real power from the given total complex power of 56.4672 kilowatts and its reactive power of 47.2896 kVAR. We will treat the angle of 39.9452 degrees as the old angle, and the new angle is equals to cos raised to negative 1 times 1. We have the condition having the power factor of unity, which is equals to 1. Reactive power for the capacitance QC equals P times the quantity tan theta old minus tan theta new. 56.4672 times 10 raised to 3 times tan 39.9452 minus tan 0 degrees. It is equals to QC equals 47.2896 kVAR. For our capacitor kVAR rating, we have to divide it by 3 to get each capacitor rating. QC equals QC over 3 equals 47.2896 times 10 raised to 3 over 3. Now, QC is equals to 15.7632 kVAR. To get the line current, IL equals S over square root of 3 VL. Here we substitute the power factor of 1 in the reactive part, which is tan cos raised to negative 1 times 1. Now our S equals P plus JQ is equals to 56.4672 plus J0. Our S, or the complex power, is equals to 56.4672 kilovolt ampere. We will substitute it to our formula for getting the line current. S over square root of 3 times VL. 56.4672 times 10 raised to 3 over square root of 3 times 840. We will get the line current of 38.8111 ampere. In number 3, the unbalanced delta load of figure 6 is supplied by balanced voltages of 200 volts in the positive sequence. Find the line currents. Take VAB as reference. We have the given line voltage 200 volts with positive sequence ABC. We use the formula of the phase currents IAB equals VAB over ZAB. Our VAB is equals to 200 bar angle 0 degrees and our ZAB is equals to 10 minus J5. We will convert the 10 minus J5 to its polar form, which is equals to 11.1803 bar angle negative 26.561 degrees. 200 bar angle 0 degrees over 11.1803 bar angle negative 26.5651 degrees is equals to 17.8886 bar angle 26.5651 degrees ampere. Next, IAC equals VAC over ZAC. 200 bar angle 0 degrees minus 60 degrees over 8 plus J6. We will convert the 8 plus J6 to its polar form, which is equals to 10 bar angle 36.8699 degrees. 200 bar angle negative 60 degrees over 10 bar angle 36.8699 degrees is equals to 20 bar angle negative 96.8699 degrees ampere. Next, for IBC equals VBC over ZBC. 200 bar angle 0 degrees minus 120 degrees over 16 bar angle 0 degrees is equals to 12.5 bar angle negative 120 degrees ampere. After we get our phase currents, we can now find our current IL or the line currents. IA equals IAB plus IAC is equals to 17.8886 bar angle 26.5651 degrees plus 20 bar angle negative 96.8699 degrees. IA is equals to 18.0484 bar angle negative 41.0655 degrees amperes. For IB equals IBA plus IBC, the value for IBA is the opposite sign of the IAB. IBA is equals to negative 17.8886 bar angle 26.5651 degrees plus IBC 12.5 bar angle negative 120 degrees. Our IB is equals to 29.1455 bar angle negative 139.7660 degrees ampere. For IC equals ICA plus ICB. For the value of ICA, it is the value of IAC but in different sign. Negative 20 bar angle negative 96.8699 degrees minus ICB, the opposite sign of the IBC, negative 12.5 bar angle negative 120 degrees. IC is now equals to 31.8757 bar angle 74.2687 degrees ampere. In number 4, find the line currents in the unbalanced three-phase circuit of figure 7 and the real power absorbed by the load. We have the given unbalanced voltage or the unbalanced sources. VAB equals to 20 bar angle negative 0 degrees RMS volts, VBC 220 bar angle 120 degrees RMS volts, VCA equals 220 bar angle negative 120 degrees RMS volts. Like in number 3, first we will find its phase currents. IAB equals VAB over ZAB. 220 bar angle 0 degrees over J5. J5 will be converted to its polar form, 5 bar angle negative 90 degrees. 220 bar angle 0 degrees over 5 bar angle negative 90 degrees is equals to 44 bar angle 90 degrees ampere. For ICA equals VCA over ZCA is equals to 220 bar angle negative 120 degrees over 10. It is equals to 22 bar angle negative 120 degrees ampere. For IBC equals VBC over ZBC, it is equals to 220 bar angle 120 degrees over J10. J10 will be converted to its polar form, 10 bar angle 90 degrees. 220 bar angle 120 degrees over 10 bar angle 90 degrees is equals to 22 bar angle 30 degrees ampere. Now we can find its line currents. IA equals IAB plus IAC. IAB is equals to 44 bar angle 90 degrees and IAC is the opposite of the ICA, which is negative 22 bar angle negative 120 degrees. 44 bar angle 90 degrees minus 22 bar angle negative 120 degrees is equals to IA equals 64.0049 bar angle 80.1039 degrees ampere. For IB equals IBA plus IBC. IBA is the opposite of the IAB. IBA is equals to negative 44 bar angle 90 degrees plus 22 bar angle 30 degrees. IB is now equal to 38.1051 bar angle negative 60 degrees ampere. For IC equals ICA plus ICB. ICA is equals to 22 bar angle negative 120 degrees plus the ICB, which is the opposite of the IBC, which is negative 22 bar angle 30 degrees. It is now equal to 22 bar angle negative 120 degrees minus 22 bar angle 30 degrees. IC is equals to 42.5007 bar angle negative 135 degrees ampere. We can find the real power, P absorbed by the load, using the formula P equals natural ICA squared times the resistor. ICA squared is equals to 22 squared times the resistor 10 ohms. Now P equals 4,840 watts or 4.840 kilowatts.